Hello, my name is Philip Henriquez, and this is my Lab 5 of Physics 2211 about the motion of a falling slinky. For this lab, we'll start with an introduction, then the theory for the lab. I'll present a tracker model, a closed script computational model for the motion, and then finish up with some observations and comparisons between the two models, and finally a what does it mean question. The main objectives for this lab is to analyze the motion of a stretched slinky falling from static equilibrium, and later compare the experimental model to a computational model using closed script so I can contrast the observed versus the predicted data. The main formulas I used for this lab are derived from Newton's second law, such as F net equals dp dt, the position update formula, the velocity update formula. I also used the gravitational force at the surface of the Earth, which is stated right here, then the force of tension, and finally the drag force. Now in this slide, we can see an actual diagram of the motion that is happening with the falling slinky. We can see that the main principle we apply here and is happening in this motion is a change in momentum as the net force is acting on the system. We have different forces, tension, pulling up, gravity, and the weight force that acts on the mass due to gravity, pulling down. And then once the slinky compresses completely, then we have the drag force and gravity acting upon the slinky. So finally, for the theory of the lab, we have the initial conditions for the experiment. This is a mixture of estimates and information found off the internet. So we assume the slinky has a mass of 0.173 kilograms. We also assume the slinky has a stretch length of 1.22 meters. This is an estimate comparing to the person in the video. The slinky has an initial velocity of 0, and the initial position, according to tracker, is stated in this page. Here we can see the experimental model I made with tracker. So in this diagram, we can see that I placed the center of mass at the bottom of the slinky. And we can see here in the diagram that tracker shows off that the center of mass stays static for the first part of the motion. And then once the slinky fully compresses, we can see right here that the center of mass starts descending and starts falling along with the slinky due to gravity. Now we move on to our second model, the closed script computational model. For this model, we can see right here the code I used, the first part of the code. We can see I used a very similar code to the one used in the second lab of a falling object due to gravity. So we plugged in the mass of the slinky, the initial position that we already had, the initial velocity we had, and then the acceleration of gravity at the surface of the Earth. And then we started with a first while loop that is 6.31 seconds, the time before the bottom of the slinky starts moving. So we have, this is the code for this first while loop that we have. Now in this page, we can see the second and final while loop I implemented in my code, which is a while loop that starts when at the time where the slinky starts falling until the end of the motion. And here we can see the code I used based on Newton's second law to calculate and gather data for this computational model. Now here we can see both graphs of the y position regarding time. The top one is the experimental model and the graph done by tracker, and the second one is a graph of the computational model by closed script. And here is a comparison of both. We can see that both follow the same trend of the center of the center of mass, which is the bottom of the slinky, staying static for the first part of the motion and then falling in the y position. We can see they have very similar trends, and they have just a small discrepancy right here. This might have been because human and experimental error when using tracker, or maybe for another unaccounted force. But in general, we had a very similar trend and a very similar motion in both the computational and experimental models. Now, finally, to finish off this lab, we'll have a what does it mean question. So the question is, Does the bottom of your model, Slinky, stay stationary just like in the video? And this actually does happen, so yes. By looking at the graph, we can see that the bottom of the Slinky remained at a constant position right here for the first part of the motion. So the net force in this part of the motion for the bottom of the Slinky would be zero. This occurs until the Slinky is pushed down by the upper part, and the Y position began to change and to fall as the weight force overcame the drag force. I hope you really enjoyed learning this lab, and thank you.